Let's go, Glasgow!
It's time for Maths with Mr. Thomas.
Chapter 12, lesson number 3. We're still with complex numbers, and we're now moving on to look at what is known as polar form. This lesson will cover the Argand diagram, the modulus, and the argument. So, let's imagine we have a complex number. Well, we know the complex numbers are made of two parts. There's a real part and an imaginary part. And we can represent complex numbers on a two-dimensional coordinate plane. So just imagine really your x-axis and your y-axis. The x-axis, what we do with that is we use that to show the real part of the complex number, and the y-axis, we use that to show the coefficient of the imaginary part, the bit in front of I. Because we are going to be plotting a complex number, well, it will be a complex plane, and the complex plane, your x-axis and your y-axis, really, we call that an Argand diagram, which looks something like this. If we have the complex number z equals x plus yi, what we do is we use the x-axis to show the real part, so we would come along x, whatever x would be, and the y-axis to show the coefficient of I, the imaginary part, so you'd go up y. So, with the complex number z equals x plus yi, you can represent that using a point. So that would be point P, or you could represent it with the position vector OP. So going from the origin to point P. What you'll notice is that instead of writing x and y for the x-axis and the y-axis, we call the axes RE for real and IM for imaginary. So this will represent the real part, and this, the y-axis, represents the imaginary part. And we do that to distinguish it from the regular Cartesian, your x, y plane. So whenever you're plotting the Argand diagram, write RE for real and IM for imaginary. Really, in general, in general, any complex number z equals, instead of x plus yi, I'm going to change that so it's a plus bi. So any complex number z equals a plus bi can be represented with the coordinates. What do you think the coordinates would be, Robert? Perfect. It would be a, b. So a is the real part, b is going to be the coefficient just of this imaginary part. So you can represent that using the coordinates a, b on your Argand diagram. Very Lord of the Rings. So your Argand diagram will look something like this. There will be a real part and an imaginary part, and because you're using the coordinates AB, it means you would come along A, and you would go up B, and that would be your point. Moving on then, so that is your Argand diagram. We need to look at two different things. One of them is known as the modulus. What is the modulus? Well, the modulus of z, so the modulus of our complex number z, a plus bi, is really the distance, the direct distance going from O, the origin, to this point. So going from O to z. And the way you write it is by using the letter R, Argand, or with z with the modulus signs either side. How could we go about working out the length of this? How could we find it? How could we find out the modulus of z? How could we get to that length? What could we use? Perfect. We can use Pythagoras. Because we know we are coming along some value a, we're going up some value b, so you would know these numbers here. You would know a and you would know b. So in order to work out r, we'll just think back hundreds and hundreds of years ago. A little guy named Pythagoras discovered that you can work out the hypotenuse of this right-angled triangle that you would end up with. So you can say that this length r would be equal to, brilliant, it would be the square root of a squared plus b squared. Or you could write down the modulus of z, so z with the modulus lines either side, and that's still going to be the square root of a squared plus b squared. So this is how you find the modulus of z. Again, the distance going from the origin up to the point that would be represented if you plotted that real part and imaginary part. That's the modulus. As well as the modulus, we also have to be able to tell what the argument of z is. And what is meant by the argument? Anybody have any ideas? The angle! Perfect! It's the size of the angle. So here, with theta, that would be your argument. The argument of z is the angle between OZ and the positive direction of your x-axis, or this axis with RE. It's denoted by arg, z, just like a pirate, or more commonly, theta. And it is such that theta goes between negative 180 degrees or 180, or between negative pi and pi if you are using radians. So what you'll really have is, if you imagine your x and your y-axis, this is the positive direction of the x-axis. So the size of the angle theta will go up here to 90 and then down to 180. But coming back the way, you would have negative, so negative 1 degree, 2 degrees and so on, to negative 90 and then negative 180. So it goes between 180 and negative 180 degrees. Note here with our real and our imaginary axes, and you can have cos theta. Well, cos theta, there's theta. Cos theta would be equal to what? A over r. Perfect, so cos theta equals a over r. If you rearrange that, multiply both sides by r, you will have a equals r cos theta. And if you think about sine theta, what would sine theta be equal to? B over r. Brilliant, so sine theta equals b over r. And if you rearrange that, b would be equal to, good, multiply both sides by r, so you would have b equals r sine theta. With our complex number, you know the general complex number, z. There's a real part, an imaginary part, so you'd have a plus bi. If we replace a with r cos theta and replace b with r sine theta, well, we end up with r cos theta plus r sine theta multiplied by I, which is more commonly written as, take out r as a common factor, and you'd have r bracket cos theta plus I sine theta. This form here is one that you need to be familiar with. And if you express your complex number, z, a plus bi, in the form r bracket cos theta plus I sine theta, it's known as expressing your number in dun, 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 polar form. Dun, dun, dun. Why do we do that? What's the point? What is the point in writing a complex number in polar form? Well, you will see in the next lesson. If it is in polar form, it is dead easy to be able to multiply and divide and find powers of complex numbers when they are expressed in polar form, which we'll look at in the next lesson and the lesson after that. But just now, what we need to be able to do is we need to be able to go from the form z equals a plus bi to r bracket cos theta plus I sine theta. So let's look at an example of each using all 1, 2, 3, 4 quadrants. Dun, 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 dun. So example 1, first quadrant. Find the modulus and argument of the complex number z equals 2 plus 2i, and hence express z in polar form. So the first thing we are thinking is, we've got this complex number, z equals 2 plus 2i. And you're perfectly right. And what we need to do is we need to take the real part. The real part would be 2. And the imaginary part, without I, you would have 2. Good, so we want to plot the point 2, 2. So you're going to have your Argand diagram. There will be the real and the imaginary. You know you would go along 2, up 2, and you will end up with this. We've gone along 2, we've gone up 2. That is where complex number z would be. That's what's represented if we go along 2 and up 2. And we know then the modulus would be the distance going from the origin up to that point that would be represented if we plotted 2, 2. To find the modulus, how do we go about doing that again? How do we find that length r, or modulus of z, if you write it down like that? Perfect, you use Pythagoras. So it'll be the square root of 2 squared plus 2 squared. Work that out, 2 squared is 4, 2 squared is still 4, so you'd have the square root of 4 add 4. Work that out, and you would end up with the square root of 8, which you could simplify then to the square root of 4 times the square root of 2. Square root of 4 is 2, and we'd still have our root 2. So you know the modulus of z would be 2 root 2. We also have to find the argument. No, we don't. Yes, we do. No, we don't. Yes, we do. And the argument is the size of the angle going from the positive direction of the x-axis, so this one here, up to this line OZ. z. So we're wanting to find that. Because it's the first quadrant, again, imagine with your quadrants, that's the positive direction of the x-axis. Your angle goes from 0 round to 180 and 0 round to negative 180. So up here, we know it's going to be between 0 and 90. So to work out the size of the argument, to work out the size of that angle, because we've got a right angle triangle, we know this side's 2, just that's the opposite. We know this side is 2 as well. That would be your adjacent, so you can just use tan. So we can say tan theta equals, well, tan is going to be the opposite over adjacent, which will be 2 divided by 2, which is 1. How do we go about working out theta then? What would theta be equal to? Brilliant, well done. So you'd have tan to the minus 1 of 1, and if you use your exact value triangles or the table that you have memorized, well, you will get 45 degrees. Perfect. So we can say then the modulus is 2 root 2 and the argument is 45 degrees. Just remember, if you write that in polar form, which we are asked to do, well, z equals r bracket cos theta plus I sine theta. We can now replace r with our 2 root 2, so we'll say z equals 2 root 2 bracket cos and theta worked out to be 45 degrees. That was the argument, so we'd have cos 45 plus I sine 45 degrees. And that would be your answer. Woo! Example 2, let's look at one that is in the second quadrant. Yeah! Find the modulus and argument of the complex number z, which is equal to negative 1 plus root 3i, and once again, hence express z in polar form. Rawr. So we've got z equals negative 1 plus root 3i. We're wanting to work out the coordinates of that if we were plotting it on our Argand diagram. So you'd have your x and your y-axis. Remember, you have RE for real and IM for imaginary. Take the real part. The real part is negative 1, so you know that really your x coordinate would be negative 1, and we're adding on root 3i. Take the coefficient of i, which is root 3, and really that's your y coordinate. So for this, we've got negative 1 root 3, which means then from the origin we would come back 1. It's going to be negative 1, and then going up root 3. Notice here I just put 1 because it's the length of the line that I'm looking at, rather than the negative 1 coordinate. So we're coming back 1, going up root 3, and then I've got OZ. That's the length from the origin up to that point that you would plot the negative 1 root 3. Remember that length, we're calling it R, and that is your modulus. It is the length, and the way you find it, well, because you've got your right-angled triangle, you can use Pythagoras! Brilliant, so you can have the square root of 1 squared plus root 3 squared, which will be the square root of 1 plus 3, which is the square root of 4, which gives you 2. Woo! So that is going to be the length of this line. To work out the size of the angle between the positive direction of the x-axis and this line OZ, well, we're going to call that theta. However, what we will do is we will work out the size of this angle. If we know that angle, that'll allow us to tell what theta is. So because the angle we're working out is not theta, I'm going to call it something else. Here, I'm just calling it alpha. So the argument is going to be, we have our right angled triangle here with this angle. The opposite is going to be root 3. Your adjacent is going to be 1. So then tan alpha will be opposite over adjacent, root 3 over 1, which is root 3. To work out alpha then, you would have tan to the minus 1 of root 3. And what's that going to be? Brilliant, you got it, 60 degrees. Fantastic. So we know this is 60 degrees. With the argument, what you always want to think is you've got the positive direction of your x-axis, and the argument always goes between 0 and 180 degrees, and 0 and negative 180 degrees. So the argument is going to lie in that range. Because we had 0 going up to 90 and then to 180, well, you can see here it lies between 90 and 180. And if we know the size of this angle we just worked out at 60, how would you get the size of this angle? What could you do, Olivia? Brilliant, just take it away from 180. So it means then that theta will be 180 degrees, take away 60 degrees, which gives you 120. So we know then the modulus will be 2 and the argument will be 120 degrees. Fantastic. We have z equals r brackets cos theta plus I sine theta. That is what we use for polar form, and all we do is we replace r, replace the modulus with the length we found, so in this case it's 2, and replace theta with the size of that angle, which will be 120 degrees. Yeah! And that will be your answer. Example 3. We're now moving on to look at, rather than the third quadrant, I'm going to look at the fourth quadrant first of all. So find the modulus and argument of the complex number z, which is 6 take away 2 root 3i, and hence express z in polar form. So we've got this complex number, and again what you need to do is you need to plot the points. What points would you plot this time? What do you think, Drew? Brilliant. So you would plot 6 because that is the real part. The real part is 6. And the imaginary part, what would that be, Vera? Brilliant. That would be negative 2 root 3. So we're wanting to plot the point 6, negative 2 root 3. Just draw out your x and your y-axis. Call the x-axis RE for real. And the y-axis will be IM for imaginary with your Argand diagram. Because you've got 6 negative 2 root 3, it means you would go along 6. And then you would go down 2 root 3. Again, what I'm doing here is rather than writing negative 2 root 3, it's more the length of the line that I'm looking at for when it comes to tan theta. So it's negative, so you're going down, but I'm not actually writing that negative in. And you know z would be over here. The length OZ is known as the modulus, and you would have R equals. Once again, to work that out, you are just going to use Pythagoras because you've got your right angle triangle. If you know this is 2 root 3 and you know this is 6, well, you can just use Pythagoras to work out the length r. So 6 squared plus 2 root 3 squared and then square root it. 6 squared will obviously be 36. And what do you get if you square 2 root 3? Well, square the 2, you get 4. Square root 3, you get 3. So 4 times 3 is 12. Add them together and that gives you 48. Don't just leave it at root 48, simplify that. So that becomes the square root of 16 times the square root of 3. Square root of 16 is 4, so you'd have 4 root 3. That will be your modulus. For the argument, what you want to think, again with the argument, is the size of the angle between the positive direction of your x-axis and that line OZ, which will be down here. Remember, your argument goes between 0 and 180 degrees and 0 and negative 180 degrees. So I know down here it's between 0 and negative 90 degrees. So that would be the angle between 0 and negative 90. I need to find that. What I want to do though first is I want to just find the size of this angle. So I'm not going to call that theta because I know theta is going to be a negative and it wouldn't really make much sense with the negative in here. So just work out the size of that angle and you're going to get a positive number. So don't call this theta yet, just call this alpha. So once again, you've got your right angled triangle and you know that tan alpha is going to be opposite over adjacent. So you would have 2 root 3 over 6, which would simplify to root 3 over root 3. And if you simplify that, well, 3 you could write as a square root of 3 times the square root of 3. So really, you'd end up with 1 over root 3. If you work out tan to the minus 1 of the 1 over root 3, or root 3 over 3, whichever way you want to write it, you end up with 30 degrees, meaning then that the size of this angle would be 30. However, with the argument, you know, if it was 30 degrees, well, 30 degrees would give you an argument up here between 0 and 90. We are down here between 0 and negative 90. So because this angle worked out to be 30 degrees, I know that is going to be negative 30 for the argument. So that's what you'd have. So we'd have a modulus of 4 root 3 and an argument of negative 30. We're writing that in polar form, and for polar form you'd have r bracket cos theta plus I sine theta. Replace r with 4 root 3 and replace the argument with negative 30. And that will be your answer when it's in polar form. Example 4, we're now going back to look at the third quadrant. So find the modulus and argument of the complex number z, which is negative 2 bracket 1 plus I, and hence express z in polar form. So what we've got is the negative root 2 multiplied by the 1 plus I. What do we have to do first of all with that? Perfect, multiply out the brackets, so that gives us a negative root 2 times 1, which is negative root 2, and it's a negative root 2 times I, which is negative root 2I. From there you can clearly see we have a real part without any i's, like granny, and we've got an imaginary part here with i's. So you would have, if you're plotting it, real part is negative root 2, and the imaginary part, take the coefficient of I, which is also negative root 2. When you're plotting that on your Argand diagram, you're going to have your real part and the imaginary part. So imagine your x and your y axis. With negative root 2, that means you're going to go back the way to the left. You're going to go back root 2. And again, for the negative, for the y, for the imaginary part, you'd have negative root 2 again. Again, I'm not writing the negatives in because I'm just looking at the length of the line. So I would have a length of root 2, even though I'm going back the way for negative root 2. And again, the same coming down. I'm coming down that root 2 length for the negative. I want to work out the length of the line OZ. That is the modulus, and it's given by R equals. And what do you use to work out that length? Pythagoras! You got it. Well done. So you would have the square root of root 2 squared plus root 2 squared. That will give you, well, if you square root 2, that just gives you 2. So if you do that twice, it just gives you 2 add 2, square root 4, which gives you 2. Woo! So that will be your modulus. For the argument, how do you work out the size of the argument? Once again, you've got your argument. It's the size of the angle between OZ and the positive direction of the x-axis. Goes between 0 and 180 and 0 and negative 180. So because we're down here, we know it's going to be a negative, and it'll be between negative 90 and negative 180 degrees. The best way to do this is to just work out the size of this acute angle. So work out the size of the angle here. That's not what the argument is going to be. So that's not what theta is going to be. So we call it something else. Again, we're just going to call it alpha. So alpha, the size of the angle in this right angle triangle, will be tan. Alpha is going to be the opposite over adjacent, which will be root 2 over root 2. Dividing root 2 by itself just gives you 1. To work out alpha then, I'd have tan to the minus 1 of 1, which is 45. Good. So I'd have alpha equals 45 degrees. Bear in mind, you are wanting the argument, and the argument is the size of theta. It's this angle here. So because I know this is 45 degrees, well, if you do it 180, take away that 45, you end up with 135. But again, because you're going between 0 and negative 90, then negative 180, I know I will have negative 135 degrees for theta, for the argument. You could always think, if this here is negative 180, I'm coming back 45 degrees, so again, it's the negative 135. Just make sure that because your line is in here, you know it's between that negative 90 and negative 180, so the negative 135 is right. So we've got a modulus of 2 and an argument of negative 135. We have to write that in polar form. Polar form is when you have your r bracket cos theta plus I sine theta. R is the modulus, which is 2. Theta is negative 135, so you'd have 2 bracket cos negative 135 plus I sine negative 135. Example 5, part A. Express the complex number 1 plus 3i over 1 take away 2i in the form x plus yi, where x and y are real numbers, and part B, hence find the modulus and argument of this complex number. So if I've got the 1 plus 3i over the 1 take away 2i, how do I go about writing that in that form? Divide! Good, I want to divide it. I want to divide that 1 plus 3i by the 1 take away 2i. And to divide complex numbers, how do you go about doing it? Oliver. Brilliant. What you do is you take the complex conjugate of the denominator. So the complex conjugate is when the real part stays the same, but you take the negative of the imaginary part. So the complex conjugate of the 1 take away 2i, well, the 1 will stay as it is, but the negative of negative 2 will be positive 2. So you'd have 1 plus 2i. And what you do is you multiply the numerator and the denominator by that complex conjugate, as we saw in the first lesson in this chapter. Doing that, just multiply out the brackets. So at the top, you'd have 1 times 1, which is 1. You'd have a plus 2i, and then a plus 3i, which is plus 5i, and then 3i times 2i will give you 6i squared. At the bottom, 1 times 1 is 1. You'd have a plus 2i take away 2i, which will cancel out, and you'd have take away 4i squared. Always remember, if you have I squared, what is I squared? Negative 1. Good. So you can replace the I squared with negative 1, which means you'd have the 6 times negative 1, which means then that'll just go to take away 6. The negative 4 times negative 1 means that will go to plus 4. Simplifying that, well, at the top you've got a 1 take away 6, so that's negative 5 plus the 5i. At the bottom, that's obviously 5. From here, the negative 5 and the 5i, divide them both by 5, so you get negative 1 plus 1i, or just negative 1 plus I. That is part A. That is us written that complex number in the form of x plus yi. We've got a real part, we've got an imaginary part. Part B. Hence, find the modulus and argument of this complex number. So to get the modulus and argument, what you need to do is you need to think, right, well, we rewrote that 1 plus 3i over 1 take away 2i in the form negative 1 plus I. So what point would we plot? Well, the real part is negative 1, and the imaginary part, how many i's? Well, just one I, so that'd just be 1. So on your Argand diagram, really with your x and your y-axis, but remember it's real, RE, and imaginary, we'd have negative 1, 1, which means we go back 1 for negative 1, and then we're going up 1. Again, not writing in the negative, I'm just looking at the length of that line. So I'm going back 1 and going up 1, so it's got a length of 1 and 1. For the modulus is given by R equals, and we've got this right-angled triangle. R then can be found by using Pythagoras. So we'd have 1 squared plus 1 squared, and then square root that, which gives us root 2. For the argument, your argument will go, it's the size of the angle between the positive direction and the x-axis and that line OZ. Again, it's between 0 and 180 and 0 and negative 180. Because it's up here, you know it's going to be between 90 and 180 degrees. Work out the size of the acute angle first of all, so that's not going to be your argument, that's not going to be theta, so we don't call it theta. We just call it something else, calling it alpha. That's the size of the angle in the right angled triangle, and we can find that using trig. So, opposite, adjacent, so tan alpha will be 1 over 1, which is just 1, and then alpha will be tan to the minus 1 of 1, which gives us 45 degrees. Because we know this is 45 degrees, well, it's the 45 degrees back from 180, so we could just do 180 take away 45, and that's what theta will be. That would be your argument, 135 degrees. So you can finish that off by saying you've got a modulus of root 2 and an argument of 135 degrees. And that is how you would do example 5. Try these questions on polar form 1, looking at the modulus and argument. Have a look at the Unit 3 booklet, page 59. Best of luck! Enjoy! Once you're confident with this, move on to polar form 2 in the next lesson. Woo! Bye!